Good morning and welcome to the LCRIG hosted webinar for Aimsun. My name is Charlotte Bromley and I am the events manager here at LCRIG. You will see a Q&A button at the top of the screen. Please put your questions in here and we will have a Q&A session at the end of the presentation to go through some of the questions received. Now that I've gone through all instructions, I'm going to hand over to your first presenter, Gavin Bailey.
Hello, thank you very much. My name's Gavin Bailey. I'm the head of business development at Aimsun for the UK and the Nordics, and shortly you'll be hearing from my colleague Tessa Hayman, who's one of our product specialists at Aimsun. Today we're going to be talking to you about using dynamic models for transport scheme appraisal. Tessa, could you go on to the next slide, please? So this work, what we're going to present to you is actually guidance which we've developed. It's Aimsun guidance which is developed in association with the Department for Transport. We've been undertaking this work for the last year or so, and it's actually what Tessa's going to take you through is extracted from and references a guidance document which is available on our website. We'll provide you all with a link to that guidance. The idea of this guidance and the work that we've been doing with the DFT is to address gaps in transport appraisal guidance that the DFT kind of administers and manages. They recognise that the guidance biases particular methodologies or types of modelling software, and they do stress that it isn't something which they want people to follow to the T. It is recommended or suggested best practice, but they encourage people to kind of use their expert opinions. Recognizing that not everyone uses the guidance in that way, we developed this guidance with the DFT to give people kind of a structured approach to using alternative modelling methods for transport scheme appraisals. As we go through this method, which Tessa's going to take you all through over the next half hour or so, hopefully we'll demonstrate, of course it uses Aimsun software, so we'll be demonstrating how Aimsun tools and models can help to address the kind of needs of transport appraisal using dynamic modelling methods. And then kind of once Tessa's finished her piece, I'll then take you through a little bit of how our models can be used both for strategic and operational purposes, so blending the two and creating a single modelling asset which serves multiple stakeholders. Just before I hand over to Tessa, it's worth kind of caveating this with this method which we're presenting to you is for use for transport appraisals, specifically for local government level appraisals. So authorities like Transport for Greater Manchester, Sheffield, they tend to use Aimsun models and dynamic modelling approaches for appraisal at their local level transport appraisals. And it can also be used for DFT level appraisals where the proposed scheme is not expected to affect demand. So could you go on to the next slide, please, Tessa? So just very briefly, for those of you who may not heard of Aimsun or may not be familiar with Aimsun, Aimsun has been around for quite a few years, around about 27 years or so. We originated from a university spin-out in Spain, and we have an international presence as a company in, so we've got offices in North America, UK, Europe, numerous offices in Europe, the Middle East, Singapore, and also Australia. And we deliver modelling services for clients across the world. You can see a few in the bottom there, with a number of our UK authorities that we work with, or authorities who use our licenses for modelling. So, for example, TFGM, we recently were commissioned by them to build a large-scale mesoscopic, microscopic model for everything within the M60, and they actually use that that model with a team of in-house Aimsun modelers. So we've got a number of authorities in the UK and a growing number of authorities who actually use Aimsun models for appraisal. Now I'm going to hand over to Tessa, who will take you through the methodology.
Hello, and nice to be talking about this topic again. I'm going to start off with very, very basic. Forgive me if this is too basic, but I just want to try and define some stuff if you're not familiar with it. So first off, what is a dynamic model? So a dynamic model is a type of transport model where things change over time. So you might have heard of a static model. A static model is generally seen as an average output over a certain period or a certain hour, so a peak hour, and it only gives one output for the whole of that time. A dynamic model has different outputs over time and different route choice over time. So a static model is usually a macroscopic model, which means that it has simplified method of understanding cost and travel time using functions of aggregate flow. So uses analytical functions where you input the flow and you output the cost at a very, very simplistic method. A dynamic model, as in this video, this is showing a mesoscopic, and it will also show a microscopic model, usually considers individual vehicles. And a dynamic model is not always, but is usually having microscopic or a mesoscopic model working out what the travel time is. And it considers individual vehicles that interact along their path, and you get a more detailed understanding of travel time due to signals or bus allocation, all those kinds of things. And as you can see, because we've got those individual vehicles making journeys, the outputs will change over time in a way that you would expect intuitively. So why would you have a dynamic model then? Most of our strategic level models are static models because they are simple and they can be built at scale with a lower runtime. However, you may want to have a dynamic model if the static model has questions that can't be answered by a static model. So for instance, if you want to have a detailed understanding of congestion, of the geometry of the network, the stacking capacity, all those kinds of things, that would be best in a microscopic model. Or you might want to look at a bus priority scheme or a cycling scheme where you're taking away the number of lanes. Again, that would be more appropriate in a dynamic model, as most static models do not have a lane-based assignment. So Gavin's given a little bit of a overview of TAG, but if you haven't heard of it or you're not 100% sure of what it is and why we're referring to it, it is guidance on the appraisal of transport schemes and given by the UK Department for Transport. However, it is widely used in the UK as a best practice document for traffic modelling, not just in areas where TAG is necessary to be applied, because there is no other transport modelling guidance out there in the same level of detail. So it is even used abroad by some users to give an understanding of what should be done. The real aim of it is to give guidance so that scheme appraisal is done in a fair way. It's not done in a biased way, and it's proportionate to the aims of the scheme test. You might have heard that there is now microsimulation guidance in TAG, which is a type of dynamic modelling, as well as activity-based and agent-based models, which often use dynamic models as well. However, this guidance is quite simplistic right now, and there's still a gap on dynamic assignment and how it can be used to give robust evidence for appraisal. So we actually started on this project before this additional guidance was given, but we still think that our guidance that we've created gives something more than the TAG guidance for dynamic modelling, because they've mainly focused on static modelling. So the main spark for this project was convergence. I was originally told as day one as a transport modeler that dynamic models don't converge. And I kind of took it for granted as that was something that you accepted. Here we're going to talk about how you can make dynamic models converge. And so first I'm going to tell you what convergence is and why it's important. So it comprises of two different things. One is stability. So this is how much a model changes between iterations. So some transport models, the route choice will change with iterations. So you can think about this as you're driving every day, and each day you think about what happened the last day and you make small adjustments to your route choice until you've come to a choice that you're happy with. The stability is checking what's the difference between day one and day two in your route. Proximity is how close you are to equilibrium, or in this analogy, how close you are to being happy with your route. So if you were to go a different way, it would be at a higher cost to yourself. Convergence happens when both of these two things are true. So you have a stable equilibrium. So you're at the optimum, so you're really happy with your low costs, and those costs aren't changing. But really, what this is about is trust. Because if you don't have convergence in your models and you compare two different models, it can be hard to work out whether the change in output, so cost or travel time, is because of instability in the network, so just because you've done another iteration, or because of the scheme. And so by having a converged model, you can be more confident that the changes are down to the scheme. Now, to set this up, I'm just going to, again, define some things. So when you build a traffic model, you have two different things interacting. You have traffic assignment. You can think about this as your route choice. And you have network loading, and this is how you calculate travel time. And every interval, you send what the travel times are on all of the roads, and then the assignment, so the route choice model, will go, okay, this is the number of people on all of these different roads based on that travel time. There are loads of different methods for those two different parts of a traffic model. What I'm going to be talking about today is dynamic user equilibrium. So this is an iterative idea, like I said, that you drive your route to work or your route to you pick up your children from school every single day, and you slowly understand what the best way to do that is. And then the network loading is a mesoscopic model. So this has individual vehicles which move step by step by step, but in a simplified manner. So it is, if you saw the video before of just the dots moving around, that can be seen as a mesoscopic model. Okay, so coming back to convergence and stability, when we had a look at this, I went, okay, I'm finally going to try and understand why dynamic models don't converge. And I worked out what one of the problems was and the stability problem that is inherent inside dynamic models. One of these examples is when you come to a signalized junction. So if you have a car here that's driving along, and say this road takes 1 second to go along it, and it arrives at a traffic light 5 seconds into the model time. It then has to wait until 15 seconds have elapsed, until the model time is 15 seconds for the signal time to go green. And this means that the travel time for this link is now 11 seconds. So that 1 of the getting across and then 10 to get out of the road. If, however, this car arrives 10 seconds later into this road, it will then arrive at a green light. And so therefore it won't be delayed at all, and the travel time will only be 1 second. This is a percentage difference of over 1,000%. And if you only have a small number of vehicles of a vehicle type moving across these links, you'll get big fluctuations in cost with only very minor changes to the arrival time of that car. There are methods to go to improve this, but having that innate understanding that the cost in a dynamic model coming from an individual vehicle means that you get these large fluctuations in cost, can help you understand how to then better improve the stability in your models. So the principles of our suggested methodology, so if this is the only thing that you get out of this is fine, are keep it simple, increase the sample size, which helps the simplicity, and make your functions smooth. Again, I will explain all of these to you. So keeping it simple is, don't think about having the most detailed transport model that you can have. Understand what is the necessary things that I need for my current scheme test and the scheme tests that might be done on this model in the future. So if you are doing a highways model, let's say of a big dual carriageway, you might go, okay, I only need to understand the HGVs and the cars. There's no route choice difference between them, but there is a lane choice difference and a speed difference. I'm just going to have 2 vehicle types. Maybe if you're doing a big city and you want to understand lane reallocation, you then might have to say, okay, I'm going to have buses, I'm going to have bikes, I'm going to have taxis. But every time you increase this number of vehicle types, you make the model much more complex and you decrease the sample size for your cost function in the next part. And then you get those larger fluctuations. So that design part at the start of your project of, I have a transport model, what does it need? Try and filter out as much as possible of going, this is what I need for the upcoming things and the lifetime of this model, rather than going, oh, I could have this and this and this, and you might not need it. Then increasing sample size. So that generally comes with keeping it simple. But think about, can you combine information from different locations to increase that sample size? Then making the functions smooth. So there are some things that we're doing on our cost functions to try and make sure we don't have the big jump, like in that signals idea that we have going from 1 second to 11 seconds. Can we make our function go smoothly from 1 to 2 to 5, slowly up to the 1 to the 11, rather than having big jumps in there? So I'm just going to be quite simple on this. There are multiple ways in dynamic user equilibrium of evaluating what travel cost means and who you're going to get information from. So with the instantaneous method, you go out of your door in the morning on your way to take your children to school, and you go, okay, this is the current travel time on all of the roads. I'm going to drive this way. That's the most simple method. The experienced method says, okay, what is the current travel time of all of the roads ahead of me right now, but only for the people making that exact same journey as me. So people from my street to that school. As you can imagine, that's going to be a very small number. And so that sample size is going to get quite small. You also have a third option, which is time dependent, which is you leave the house and open the door and you say, what's the current road conditions and what will the traffic light be when I get there? So in 20 minutes time, when I get to a junction 20 minutes away, what's the travel time going to be? Again, that sample size is quite high, so we don't have to worry about it. So one of our recommendations is to only use this instantaneous or the time dependent method. So again, trying to think about big samples. Okay, then one of the problems we had with our models when we had a look after understanding these general approaches is we had unstable travel times due to low flows and signals. So that's something I showed. So one of our solutions was to use analytical functions and pass the travel time from other sources. So it's not very clear here in this chart, but the idea is that if the flow on a link is less than, say, 20 or 30 vehicles, instead of using the dynamic cost, you can instead use the analytical costs that are used in static models. This is quite appropriate when you've got the low flows. You don't have the problem of congestion, and we can then analyze the expected delay at a signal rather than the actual individual vehicles that have been sampled that are quite low sample. We could go, okay, this is the expected delay at a junction. So if you have a 30 seconds green and 30 seconds red, you might say, okay, on average, per person's going to wait 30 seconds, whatever. There is a bit more complexity to that. But the other thing we might do is if there is enough information from another vehicle type, we might take that information from that vehicle type. So if we've got taxis, for instance, and we've only got one taxi, we might go, okay, well, I'm going to take the information from the cars. That is a reasonable estimate for the taxi. The next thing we looked at, which is for the same reason, is averaging the cost over multiple iterations. So this increases that sample size. We're using the exponential average, taking the travel time from previous iterations and averaging those. Because when you make that decision, you leave the house, you don't just think, okay, what's it like right now? You also take into account the memory for the past month that you've been driving this route. And so you might go, aha, this says that the travel time is really low, but I know that everyone else is going to make that same decision and it gets very, very congested. So I'm going to take a more robust route. That takes this into account. The next thing that we recommended is using a warm start. So a problem in dynamic models is that you get quite complex route choice, and there are multiple what we call local optimums. So there's not just one optimum output, there are multiple ones. So therefore, we can end up with quite a lot of noise, even though both of them are in equilibrium. We therefore recommend using an input path assignment as a starting point. So you have your base model, and your base model should be run to near equilibrium. And then you could use that as a starting point for your schemes. Your schemes will then change their route choice according to their base model, according to the COTS changes from the scheme. But they'll be using the inspiration from that base path assignment. So for the flows that aren't affected by the scheme, you'd expect that they change very minimally. We then had a problem that we made the assignment too stable, even when it was gridlocked. So what we did is we took a look at the step size. So when we're trying to calculate the optimum routes for a vehicle, what we're kind of doing is we're thinking about how we get to this optimum. You can think about this as when you're climbing a hill. If you want to get to the peak, you can look around you in all directions and go, which is the steepest direction, and climb a couple of steps in the steepest direction. And then as you get closer and closer to your top of your hill, you might take smaller and smaller steps. And theoretically, at some point, that should guarantee that you get to the top of that hill. We have the same thing. So we have the gradient algorithm. And what we did is we looked at that step size and we said, okay, we're going to make sure that we keep the step size small if we're inheriting the routes from another model. And that means that you're making small adjustments because you're near equilibrium. The other thing that we did is we then decided to reset the step size when the R gap exceeds a certain variable. The R gap is a measure of how close you are to equilibrium, how close you are to the top of that hill. So when it exceeds a certain variable for an origin destination, we allow that the vehicles making the trips from that origin destination to make big changes. When we also, for vehicles directly passing through a scheme assessment, those will get reset. Because obviously if they're driving through that junction, they're the ones that are most likely to make big changes to their network and not big changes to their route choice. Then the final part of our methodology is we had problems with the stability of route choice in all areas of the model. So what we did is we wanted to add a target R gap. So again, that's that target variable of seeing how close you are to the top of the hill per OD pair as an OD matrix. And this means we can target where the convergence should be tighter, for instance, around the scheme, but also that gradient algorithm can concentrate on the worst parts of the model. So here's an example of how this works. We've got a target OD matrix for the R gap, and here's the output. So if we look at 1-to-1, in the first iteration, we have 0.1. That is less than 0.5. So therefore, in the next iteration, those paths don't get updated because they're close enough to equilibrium. If, however, in the next iteration, a vehicle arrives at a signal or something very differently, or it has some different interactions along the way so that route choice is no longer the best. So here the R gap has gone to 0.6. Now that's greater than 0.5. We then might say, okay, you can change that path. All right, so coming off the theory, let's put it into practice. We used this methodology on a test model. So a model of Barnsley, it was a mesoscopic model that we created for this project. And we looked at this junction here. Now I'm going to say this scheme that was created is not a real scheme that's necessarily going to happen. It was just, I wanted to test a scheme here to understand, can we make the outputs for this scheme localized to this area rather than across the whole network. So the scheme it's relatively minor, moving these. So you have increasing the stacking capacity to the south and to the north of this junction. Again, I'm going to say the signals here were not optimized. So here, what we can mostly summarize is that there was a change to this junction and that one only. So to evaluate this, I looked at the difference in assigned turns and sections flow, the difference in link average travel times as a function component. This is just a thing inside Aimsun Next. The difference in average travel time per OD pair, and the sector to sector average travel time. So that is like your MSOA to MSOA kind of output. So first I looked at the outputs at the OD pair level, and I saw that it wasn't sufficiently stable as the largest changes weren't located at the scheme. So if we look here, we've got the red and pink lines. These are the OD pairs that had the biggest changes. And you can see the junction down at the bottom where we put the change is not where the biggest changes are happening. So here, by testing the stability, I actually found that there were some problems in the model I'd created. I had a missing centroid connector in the geometry configuration, and I had several OD pairs with too loose of an R gap at the OD pair level. So I changed the R gap matrix and went again. So after fixing these, I got some good outputs. So the first graph is your R gap, how close you are to equilibrium. This is coming down nicely. The second two graphs are two variables indicated by tag of stability, which is the number of, the percentage of links with a flow variation below 1% and the percentage of links with a flow variation of, cost variation of less than 1%. And tag's target is that 98% of links have a flow and cost variation of less than 1%. And this was achieved after fixing those connections. I then looked again at the largest changes in the travel time skid matrix, and now my OD pair changes are localized to that junction. So I'm happy with that. And I then looked at the turn-based flow and travel time, and I saw that there's still quite a lot of noise, even when we're removing the vehicles, the flows with less than 5 vehicles. So what we did is, this is when I integrated the analytical function at low flows. And this was achieved when we've got a tight convergence. So here's the results of the full methodology. We've got the R gap coming down in both the base and scheme. The percentage of flow, so the percentage of links that have a flow variation below a certain level, is now at the standards specified by tag. Although we do recommend a lower level for flow can be useful. The reason being that if you have a flow of 100 vehicles per hour, tag says you can have 1 vehicle's difference. And that means that for a lot of low flow areas, you basically need 100% the same flow. So some variation is recommended in our methodology on that. Then the cost. So again, we see our cost is reaching those levels. Looking at the skim matrix, the changes in travel time for origin destination pair were localized around this junction. The proportional difference in link flows, again, were concentrated around this area. although as it was a proportional difference, you do see some difference in the low flow areas. But if we look more at travel time, that travel time is more focused in this area. So we ended up with having a dynamic model that we think is capable for use for scheme testing in large scale dynamic models. This one is relatively small, but you can use this methodology in some much larger models. So we're using it actively at the moment in our Manchester model. And we think it's something that will enable you to create really highly stable models with a methodology that allows you to check for that. We have got some further steps, so this isn't finished. We're going to be doing lots of different things to try and improve this. Our next step will be testing the model with Tuba and ensuring that not just our OD pair travel times are stable, but our economic outputs as well. Okay, back to Gavin.
Thank you very much, Tessa. Right, so I'll just go over a couple of Aimsun tools and briefly over the software for your interest. So Tessa, could you go to the next slide, please? Right, so just in terms of Aimsun Next, so Aimsun Next is the software which we develop and we license out. But that is surrounded by a number of other solutions, which digital solutions which we provide. Aimsun does actually provide modelling, professional services, kind of modelling to authorities and also to private companies alike. The Aimsun Next kind of software is a single piece of software which enables modelling of transport networks at multiple at various scales within the same piece of software. So you can model hybrid environments. So you can model mesoscopic, macroscopic, and also microscopic, all within the same application, zooming in and out of different areas of the model. The benefit of that actual feature is that it's all integrated into a single solution. You don't have errors kind of creeping in by moving stuff between different modeling files, between different applications. And that actually also critically enables some of our other digital solutions, like our traffic digital twin, which means that you can actually have everything in one place. You can have a strategic modeling tool, and you can also have an operational modeling tool. All of that, of course, helps to improve the consistency of modeling approaches, and also kind of the asset as a single thing. With this tool, if you can go on to the next slide, Tessa, you can hit multiple stakeholders. I mentioned that we provide professional services for modeling, and we also provide a number of digital mobility solutions. I'm not going to cover all of them, but just kind of cover the ones which are relevant to strategic modeling in the context of this webinar. So we have what we call Aimsun Insight, which is a data analysis tool. And these use cases are what we've seen it previously applied to, and what we also consider it could be applied to where it hasn't. So we, as a company, undertake a lot of research funded by the EU, also the UK governments. So we use these tools in those kind of research projects. So we're also exploring how these tools and solutions can be used potentially to meet future needs. If you could go into the next slide, please, Tessa. I think we've got an example of our data insight. So our data insight solution is a machine learning driven solution. And what we do here is we take data, continuous traffic data from sensors in the traffic environment. So this may be scoot loops, mover loops, Viva City detectors. We can also take floating car data. Provided we have a minimum of 3 months worth of data, ideally a year's worth of data, we can deploy the algorithm, and it will interrogate the data, the first thing it does is it looks at the data to understand anomalies and spurious data within that data set, and it can actually uplift that data set by imputing and interpolating values. I think if you press next, Tessa, it will take it to the next. So there, on that previous graph, we had the detectors down the side and then the days of the year along the bottom, and you saw the black areas which were kind of bad data. It was 0 values or negative values, and green is good, red is kind of poor data. So here you can see that we've actually uplifted the data, we've improved the data set using statistical AI methods, basically. Once we've cleaned the data set, we can then extract patterns from that data. So if you go on to the next slide, it should have a back one, please. Thank you. We can actually extract patterns from that. And one of the interesting things that we've found in our work with Tees Valley in deploying a traffic digital twin, and also our more recent work with Transport for Greater Manchester, is that this method of data-driven pattern extraction, which doesn't involve a human user in identifying the patterns, is it actually removes the identification of patterns from any potential biases that users might have. The main one that we found is that when we've actually taken this data for the authorities, we presented it to planners for use in strategic modelling, and this is where we see one of these clear applications for this, is that there was a general perception that Mondays were very different days on the week due to COVID, but actually when we look at the data, Fridays are the day which have changed both across Tees Valley and also Manchester in terms of travel patterns. So just to rewind a little bit, then we've got our algorithm pulls out traffic patterns for the days. So you've got on the left-hand graph your kind of morning peak, your and then your evening peak on some of those patterns, and then it transposes that onto a year. And the most that we do with this is we restrict the number of patterns that it will generate, because the last thing you want is 365 patterns. It's not of use to anyone. But what we can do here is we can actually pull out, this is emergent from the data, the patterns across the year that you might expect to see. You can see Saturday and Sunday there is a clear, and Friday there are clearly different patterns or distinct patterns defining those days throughout the year. And then you can see some of the seasonal variation related to bank holidays. So you've got Christmas and New Year up in the bottom and the top right hand corners. If we were to allow a few more patterns to be generated, then you'll see a bit more seasonal variation across the months. So you'll see some horizontal blocks of colour as well. Could you go on to the next slide, please, Tessa? I think this is one of the last slides. So what we're trying to get across with this webinar is, of course, we're trying to demonstrate that there is a methodology, there's a valid methodology for use of dynamic simulation, traffic simulation for transport appraisals, scheme appraisals, and you can yield those the benefits of dynamic modelling in, theoretically it's meant to better represent traffic behaviours and how traffic networks will react to changes on road. But in building dynamic models and using Aimsun models for strategic modeling, you can actually start to create a single asset which can address your strategic needs, which are kind of those scheme testing and also potentially signal emulation up in the top of the stakeholder wheel. And then you can start to address your operational needs by extending that model into connecting it to real-time data, and then using it as an operational asset for traffic management, and then building in automations for bus reliability improvements. We're deploying that tool in Tees Valley. You can use it for improved incident response planning and management. And the idea here is that it's to try and demonstrate that with a single modeling asset, you don't just have to create that, do an update of a strategic model every few years or so when you need it. You can actually have that. You can create one and then you can continue to maintain it and use it as an operational tool. And by using it as an operational tool, that map and that model is continually updated so that when you come back to strategic planning, you can actually pick up an asset which is already there, already up to date, needs very little calibration and validation, and you can actually go back and you can use it for scheme testing. So you've got this asset where you can smear the costs of strategic and operational needs across the two and keep it going, and also yield multiple benefits in the operational domain. Could you move on to the next slide, please? So where next? Well, in terms of our work on this guidance, we're continuing, as Tessa said, we're continuing to explore the value of this methodology with a tuber, with some transport user benefits analysis. And we are also continuing to work with the DFT to understand how dynamic models can be used for schemes where they are expected to affect demand. This is a much larger piece of work. It actually starts to stretch into the academic field a little bit. So the timescales on this we expect might be a little bit longer, but it's just to let you know that we are continuing to work in this area. We think it's important for the field, particularly when you start to look at modeling concepts like activity-based modeling or agent-based modeling, which could also benefit from that. And of course, we saw a very light update to TAG, which referenced those types of modeling. But if you're interested in having a look at Aimsun Next software and having a play with it, and just kind of getting a feel for it, and also exploring dynamic modeling, we do have a free 30-day trial, which is available on our website. If you go to aimsun.com/free trial, it's there on the slides. I think the slides will be made available to all attendees for reference. Then please go there and you can trial the software. And you can also please feel free to contact myself or Tessa with further questions or for training if it's something which you're interested in after you've had a play on the software. So we won't take up any more of your time. Thank you very much. If there's any, I think we've got a couple questions in the Q&A, and please feel free to kind of add some in as we go, and then once we've gone through those, we'll wrap up.
Yeah.
So Tessa, I think we've got one question from Charlotte Johnson there.
Yep. So she's asking, can you make a static model dynamic? And if so, how can you do this, potentially just for one area or route? So yes, we can do this. There are multiple ways to do it. So I'll give you some. It all kind of depends on what your model purpose is for, on how you'd go about this. So if you're looking to potentially upgrade the whole model, we can import inside Aimsun Next, we can import files from Saturn and from Visum, and that doesn't include that includes not just the network, the control plans and the matrices, but includes the cost functions as well. So we can not a 100% one-to-one ratio, but we can model a lot of stuff in the same way as your original model, and then calibrate it to that, and then start to convert it to a dynamic model. What you can also do is you can combine different methods of route choice inside Aimsun Next. So you can have most of your vehicles following a static route choice, and a small amount of your vehicles following a dynamic traffic assignment of some sort. You can't combine this with dynamic user equilibrium in the same way, but if that was something you wanted to do, we can talk about the ways we could do that for you. The other way of doing it is to use macroscopic network loading. So the same way that you're doing analytical cost functions in some areas of the network, and to use mesoscopic modeling in other areas. We call this hybrid macro-meso. And so the whole of the model will have dynamic route choice, but parts of the areas will have simplified methods of calculating travel time and other methods not. So you can think about this as, if you're, I don't know if you're familiar with Saturn, but if you have, in Saturn, you have your buffer area and your more detailed area. We can do a very, very similar method where we can have a mesoscopic area of detail and a buffer area around that. Again, if you want any more detailed design for your question, just come chat to us and we can give you some of the options there for you.
Fantastic. Thank you very much. I don't think we've got any other questions. If you do, please type them in now. Otherwise, please feel free to get in touch with us on email. I think on the next slide, if you go on to that, Tessa, please. You can find my email there. We've got another post. From Paul Furman, is it possible to model park and ride journeys in Aimsun, because that is basically a private and public mode choice?
So not in the dynamic ones, so that's a demand question, but yes, if you're using Aimsun Next for 4-step demand modeling, you can do park and ride in a similar way to you do in Cube or other softwares.
Okay. Thank you very much. Well, unless there are any other questions, as I said, please feel free to direct them to me, and I can forward them on to Tessa. Otherwise, thank you very much for your time, and I hope you enjoyed the webinar.
Thanks, Gavin. I'd like to thank you all for attending today. For further information on other webinars that we are running, please keep an eye on our weekly newsletter. Thank you and enjoy the rest of your day.